In our favorite sci-fi stories, traversing the galaxy is as simple as pushing a lever. You engage the warp drive, the stars stretch into long white streaks, and you are instantly light years away. But when we look up at a universe that spans roughly 150 billion light years across, we are painfully stuck in the cosmic slow lane. Our fastest probes take decades just to leave our own solar system. So imagine we miraculously engineer an engine capable of hitting the speed of light. What would actually happen to a human body the second an astronaut stomped on the gas? The reality is that the universe enforces a strict, absolute speed limit. Any attempt to reach it is met by the unforgiving laws of human biology and physics. If you try to accelerate to light speed in just a few seconds, you run into the first barrier. The human body would be slammed with a force of over 6,000 Gs. At that level of acceleration, your heart cannot pump blood upward against the crushing force. Your blood instantly pools in your lower extremities, starving your brain of oxygen, before the sheer physical pressure flattens you entirely. To survive the trip, you would have to accelerate at a rate the human cardiovascular system evolved to handle, about 1 G, or the standard pull of Earth's gravity. But at a comfortable 1 G, it would take nearly a full year of constant, uninterrupted thrust just to reach the speed of light. Surviving in space for that long introduces new threats. Even aboard the International Space Station, astronauts face severe disruptions to their homeostasis, suffering from steady muscular atrophy and bone degradation the longer they remain in microgravity. Whether by instantaneous crushing or slow physical degradation, our cardiovascular and musculoskeletal systems prohibit surviving the acceleration profile needed to reach the cosmic speed limit. Let's assume you bypass biology entirely. Imagine you are encased in a theoretical robotic suit that keeps you perfectly intact. You immediately crash into the next wall, Albert Einstein's theory of special relativity. This is the Lorentz factor mathematical equation. It dictates a strange rule of the physical universe. As a spacecraft accelerates closer to the speed of light, its relativistic mass begins to increase. Look closely at the denominator here, specifically the velocity squared over the speed of light squared. Because of how this equation scales, pushing a relatively tiny 10-ton ship to 99% of light speed would require 200 times the total amount of energy consumed on Earth in an entire year. If you try to squeeze out that final 1% to reach exactly the speed of light, your ship's mass approaches infinity. Moving an infinitely massive object requires an infinite amount of energy. This is exactly why we can only propel objects to near light speed inside massive machines like the Large Hadron Collider. We can push subatomic particles to 99.9999% the speed of light, specifically because their mass is incredibly tiny. E equals mc squared operates as a physical barricade. The principles of special relativity dictate that anything with mass is barred from reaching the absolute limit of c. But theoretical physicists have proposed a workaround. Enter the Alcubierre drive, the mathematical equivalent of a sci-fi warp drive, designed to cheat the speed limit by bending space rather than moving through it. Instead of accelerating the ship itself, this drive creates a localized bubble of flat space. It moves forward by compressing space-time in front of it and expanding the space behind it, surfing a geometric wave through the cosmos. The mechanics of this work on paper, but powering that bubble requires exotic matter, a theoretical substance with negative energy. Early calculations showed you would need a sphere of exotic matter, roughly the mass of Jupiter, just to power a small ship. Even if we could harvest a Jupiter-sized battery of negative mass, the physics of the bubble itself turn hostile. The drive generates extreme temperatures via Hawking radiation that would instantly incinerate the crew inside. Meanwhile, the front of the bubble collects high-energy particles during transit, unleashing a deadly blast of blue-shifted radiation that would obliterate whatever destination you arrived at. So, while warp drives offer an elegant mathematical loophole, subjecting them to the real-world conditions of radiation and energy density makes them instantly lethal. This leaves us with a harsh truth. If you have mass, you are permanently banned from traveling at exactly 299,792,458 meters per second. And the closer you get to that number, the more time bends around you. Because of time dilation, an astronaut moving at relativistic speeds will age significantly slower than everyone left back on Earth. We actually see tiny fractions of this effect today in astronauts like Scott Kelly after extended orbital missions. This textbook identifies light speed as the absolute limit of causality, the maximum speed at which any influence in the universe can travel from point A to point B. Causality is the principle that a cause must always precede its effect. Because relativity proves that the timing of events depends on the observer's motion, traveling faster than light would allow a pilot to reach a destination before their own departure signal even arrived. By outpacing its own history, an FTL ship would deliver an effect before its cause, destroying the logical sequence of history. The physical laws of our reality demand immense patience. Humanity will eventually spread out and explore the stars, but doing so will require multi-generational ships and sustainable engineering, moving at a pace that respects the unbreakable logic of the cosmos.